morning, everyone. So let's continue with the next talk. So after this great introduction of photovoltaics from Professor Juan Bisquer, let's continue trying to understand another important topic when we want to build a device, which is the metal semiconductor interface. And the best person to do that is next speaker, Professor Andreas Klein. So all the research career of Andreas is about semiconducting materials. He started working on two-dimensional chalcogenides in his master thesis, and then he became an expert on surface science techniques, mainly XPS, during his PhD in Berlin. So a very remarkable result of Professor Andreas Klein and his team is that they were the first to measure the band structure of a single layer of tungsten disulfide. In 1998, he moved to Darmstadt, where he's now a professor, the Technical University of Darmstadt, first as a postdoc, and then become a group leader and associate professor in 2008. He worked more than 15 years on thin film solar cells and their interfaces, mainly CIGS and cadmium telluride, learning about the importance of defects and interface properties. Then he started working on transparent conducting oxides, zinc oxide, ITO, and he's still working on these systems and doing extremely meticulous work on surface, interface properties, and more on the field of defects, such as oxygen diffusion, surface oxygen exchange, and how these defects affect the electrical properties. More recently, he's combining his knowledge on semiconductor physics, surface, interface, and defect properties to apply what he calls Fermi-level engineering to other functional oxides, such as ferroelectrics and ionic conductors. So lastly, on this topic, he won a super big research project on anti-ferroelectrics with 12 PI, funded by the state of Hesse. So Andreas, the screen is yours.
Thank you, Mariona. Thank you for the nice introduction. And also thanks. All right. Yeah, you should stop screen sharing, Mariona.
Yeah, no, sorry.
And I want, yeah. Okay. And I also like to thank Ignasi and Pep for inviting me to give this talk at the school here. Well, it's quite a challenge to give a talk for a school, but when you are really in very close to a field where the audience is really interested in, because you'll always be tempted to present your science and to be less pedagogical. So I hope what I have prepared is a good combination of the two. Okay, so I modified the title a little bit, but because I think it's not only about semiconductor metal junctions, it's also about junctions between semiconductors and semiconductors. So we do these experiments, we use XPS for doing that, and we learned a lot about the materials, particularly about oxides, and that is what the talk will be about today. So the laser pointer is here, yeah, and to switch the slide is that. Well, I will talk about energy band alignment first. The first speaker, Juan Bisquer, he already introduced a lot, was talking a lot about this. Just again, give the definitions and the relevant quantities for that. I will then show you how we determine this by XPS. I will do this at the beginning because I will show some examples in between these different topics, and it would be good to understand a little bit how that is done. So historically, the barrier formation between metals and semiconductor was first addressed by looking at the alignment of the energy levels, in particularly the alignment of the vacuum energy, which is called, that was done by Mott and by Schottky, and that's why this is called the Mott-Schottky rule. More later, the people have realized, actually not really much later, people have realized that the Schottky barriers, so the barrier heights at these metal semiconductor junctions, do not really follow what is expected from this vacuum level alignment. And this was a term which was then, this observation was then called Fermi level pinning. And starting in the late 60s, but mostly by work in the 70s and the 80s of the last century, it became clear that the charge neutrality levels and induced interface states are really important for the barrier formation for the band alignment. But that's something which was relevant for the materials which were mostly of interest for the community at that time. And these are, of course, semiconductors like silicon or gallium arsenide. These materials have a quite strong covalent character of their chemical bonds. And I will show you that this Fermi level pinning by this induced gap states is something which is particularly important for these covalent semiconductors, and it's less, or in principle not relevant for the ionically bonded materials. That includes the chalcogenides and it includes the oxides. Actually, that's a good thing for the chalcogenides because that's really one of the reasons why these materials work so nice as thin film solar cell materials. Still, even if we say that the intrinsic pinning is not present in the ionic semiconductors, there is a pinning, and this pinning is induced by defects because in contrast to the covalent semiconductors, it's usually very easy to form a defect. Let's, for example, say a vacancy or something like that in a more ionic semiconductor. And these also influence the band alignment, the effective band alignment and the barrier heights. And particularly when it comes to transition metal oxides, you will see that that can have quite some severe consequences for let's say they confine the Fermi energy, and that can have some severe consequences for any photovoltaic applications. All right, so this is in principle a graph which was shown by Johan Biskert. And that is about what is the contact for an ideal solar cell. So we have this selective contact. This would be a contact which is selective for electrons. And this is a contact which is selective for holes. Yeah. So there was the question to Johan, what makes these contacts selective? And of course, as it is shown here, the contact is in principle not selective. If you photoexcite an electron-hole pair, the electron can go to this side, but it can also go to this side. So there is no obstacle for that. And the same for the holes. So the holes in the valence band, they can of course go to this contact, but they would also win some energy when going to this contact. So this does not give the selectivity. Usually, if you want to make the contacts selective, what you have to do, you have to add an additional barrier here, a blocking layer for holes, or on this side, a blocking layer for electrons. This is not shown in this graph, but that is the reason, that's in principle the secret which makes the contact selective. In a silicon solar cell where you have a PN diode, this is not necessary because the material itself is forming the selectivity, and that's because of the diffusion length. So you will have the photo-generated holes deep in, if you do illumination from here, this side, the photo-generated electrons, in principle, you hardly have any of them at the back contact, and you will hardly have any holes at the front contact because you have a very high electron concentration here. So then it's the doping and the nature of the PN junction which makes the contact selective for the PN diode. So that's kind of a different thing. Anyway, but if we take this simplified picture, we say this is the splitting of the quasi-Fermi levels, Fermi level of the electrons and the Fermi level of the holes. And the splitting of them, that gives us the photovoltage, and the splitting is limited by the difference of the Fermi energy at the contacts. So on this side, we have a Fermi energy which is high. That means far away from the valence band. This Fermi energy is low. It's close to the valence band. Wait, I'm gonna, yeah. Does somebody know how I can open the chat window? Because when I am in the full screen mode of the presentation, I cannot see the chat window, and they had the same problem the last talk, because that would give me the opportunity to see any questions once they come up directly. I guess I have it. Yeah, great. Yeah. So that means if I may identify some questions coming up there now. Okay, good. Thanks.
If not, Andreas, then in 40 minutes, there will be a 10 minutes break where people can ask. And at the end, we will have 30 more minutes.
Yeah. I have some summary slides after the different sections, and we can use also these for asking questions. So that will be 3 or 4 short summaries in between, and we can take this as a question. But you can also ask questions in between. I think is it possible for the attendants to unmute themselves and just scream and say, I have a question? It would be fine for me. So
yes, they can do this.
Oh, that's good. So that means if you have a question, and even if it's already for the slide before, just unmute yourself and say, I have a question, and then we can go along with that also. Yeah. So we don't need to. In principle, we can do this verbally and not only by chat. All right. So that's the contact behavior. We need a high and a low Fermi energy. And the question is, what do we have to do in order to get that? Oops. All right. So we are talking about Schottky contacts. So that means we have a semiconductor with a valence band maximum and a conduction band minimum. You will notice that there is no vacuum level here, because that's not relevant for the barrier and for the electrical properties at all. Then we have a metal, and for the metal, we don't draw the valence and conduction band. We, in principle, simply draw a line, which is the Fermi energy. That's the highest occupied state in the metal. If we bring that into contact, the Fermi level arranges itself somewhere inside, usually somewhere inside the band gap. And that gives us this distance, so the Fermi level position at the interface. This gives us the barrier height. So that's the barrier height for the electron. And it's the barrier height because if an electron wants to go from the metal, it is at an energy, it has an energy close to the Fermi energy. If it wants to go to the semiconductor, it cannot go here because there are no electronic states. It has to go over the barrier. It has to go into the conduction band. So that's really a potential barrier. The same for the holes. You have a potential barrier for the holes, and the whole barrier height for the holes is this one. Yeah. So, and the sum of the two, that's simply the band gap. So that is, if you measure barrier height for electron and barrier heights for holes, and the sum is not the band gap, something is strange. Okay, so that is something what is important, and the people usually don't understand this language, or very often do not understand the language, but the best definition of the Schottky barrier height is that it corresponds to the Fermi energy position at the interface. Well, now there was no doping of the semiconductor, but you can easily add that. Take this interface, this semiconductor and this metal, and you make the semiconductor now n-doped, you get a band bending in the metal. And if you make the semiconductor p-doped, you get a band bending in the semiconductor here. If you make it p-doped, you get an opposite band bending. So, but you see that the distance between the Fermi level at the interface is the same in both cases. And it's also the same as in this case where there is no band bending at all. And that's something which is very important. You can dope your material however you want. And that means the barrier height does not depend on the doping. That is also something one partially has to argue, that the people say that if you do a different doping, you get different barrier heights, but that's not true. What is different, of course, is the band bending. If you change your Fermi level, if you change your doping concentration, the Fermi level in the bulk will be different, but the Fermi level at the interface, not. It should always be the same. Okay, what does that mean, these lines, the conduction band and the valence band and the Fermi level? What is that? And that's, in principle, is a representation of all electronic states of the material. So that's the band structure of a semiconductor. You see here, this is for silicon, that's from a book. And you have the valence band maximum is here and the conduction band minimum is here. So if you want to move these levels, the conduction band and the valence band, in principle, you have to move all electronic states. But the Fermi level is something which can very easily vary in the band gap, because the very small concentrations of dopants can shift the Fermi level quite a lot. Now that's a band structure of a metal. Yeah, that's copper, because you see here the S band and you see here the flat, these are the D bands of the copper. And the Fermi energy is here. And the Fermi energy is fixed because it's given by the number of electrons. So each copper gives 1 electron into the S band and 10 electrons into the D bands. And that means the occupation of the states is really fixed. So this Fermi level, this line we show here is just a representation of all electronic states in the copper. And now we make the contact, and I have to leave now the presentation mode. Sorry. Because now we go into contact. So we bring the Fermi level somewhere in the contact with the semiconductor. And if you would change the Schottky barrier height, that means you would have to change all electronic states. So, and you can imagine that that's something which is not easily done. That means you have to change the chemical bonds at the interface. So, and that gives us, or in principle, you change the electronic states at the surface. So that means if you fix the composition of your metal and the composition of your semiconductor, the Schottky barrier height is fixed. So for a given combination of materials, your Schottky barrier should be a unique quantity. All right. Okay, so, and similar things apply for the heterojunctions. So the heterojunction offsets, we take 2 semiconductors with different valence and conduction bands. So they have different band gaps, and now we bring them into contact. And we have now a discontinuity in the valence band and a discontinuity in the conduction band. So these are also called offsets. And that's also something which is, these quantities are also unique to any material combination. So if you take, for example, gallium arsenide and aluminum arsenide, you will get in principle a unique alignment with a fixed valence band and conduction band discontinuity. Now that's again without Fermi level, but the Fermi level is not important. That means the doping of the bulk of the materials is not relevant for this alignment. So you can do, for example, a PN junction. That would be a typical energy band diagram for a thin film solar cell with a smaller band gap p-type material and a wide band gap n-type material. You have 2 discontinuities here. Or you can make both materials n-type. What you then get is you get here, in principle, a 2-dimensional electron gas at the interface. And as for the Schottky barriers, these discontinuities are always the same. So they should not depend on the doping of the semiconductors. And the discontinuities just, they are the important quantities. Okay, so now how do we determine that? We do that by XPS, X-ray photoelectron spectroscopy. So this is not the, this is for the reference for the certain specific experiments will pop up there. So we have an XPS system. This is a monochromator, so we get a nicer, sharper X-ray line, and this is our electron analyzer. This is some other equipment there. This is our sample distribution chamber, a load lock, and then we have several deposition chambers of a material. So we bring in our material into one of the chambers, and if we have an oxide, we heat it a little bit in the vacuum or with some oxygen, and then we have a clean surface. So the surface preparation, the surface cleaning is the first step. Then we go to the XPS and do the analysis. After this, we go to our chamber and do a deposition. Then we go back to the XPS and do the analysis. We do another deposition, we go back to the analysis and so on. And then after a certain number of deposition steps, the experiment is completed. So such a typical experiment may take 1 to 2 days. That depends a little bit on the deposition temperature. And if we can identify the band alignment and the interface chemistry. So one has to say that the deposition of the layer has to be very thin, because if you put 5 nanometers of your material on top, you don't see the substrate signals anymore. So what we usually do, we deposit films with, let's say, 0.1, 0.2, 0.5 nanometers and so on. And that can be easily done with our system. So that should be not a problem. Okay, so that's just an example. This is what happens when you deposit platinum on a PCT, so lead circonate titanate thin film. So the red one, this is the original spectrum. So this is the clean PCT substrate. There is no platinum. There is an oxygen, there is a titanium, there's a zirconium, and there is the lead peak. So these 2 peaks always there. This is the spin orbit splitting of these levels. So the oxygen 1s doesn't have the spin orbit splitting. Now you deposit platinum on top and you see how the platinum is getting more and more, and all the oxygen, titanium, zirconium, and the lead disappear. There's already, you see that the deposition of the platinum, already the lead peak is split into 2 components. And that one here, which arises here, this is a metallic lead peak. And that is because the platinum itself is reducing the oxide. That's something which will come later. Okay, so what's the difference when we do a photo emission of a metal and of a semiconductor? So if you have a metal material, so here are your valence bands, here is a core level, here is the secondary electron edge. So this is where the kinetic energy of the electrons is 0. In the metal, the states are occupied until the Fermi energy. Now with photo emission means we illuminate our sample with X-rays, electrons are emitted. So we can only measure occupied states. So the Fermi level is the highest possible state we can observe in the material. The unoccupied states, you have to do other techniques like X-ray absorption, and which is not possible in the laboratory. You can do it at a synchrotron. Then you will also get unoccupied states. In a semiconductor, the Fermi level is somewhere in the band gap. And then you see that this valence band maximum is now, the maximum of the valence band states is now below the Fermi energy. So that's the difference between the semiconductor and the metal. Okay. And now we look at the binding energy calibration of our XPS. So the situation here, this is maybe our vacuum level. This is our core level of the electron. This is somewhere the Fermi level in our material. And we want to know this. This is the binding energy. And we want to know this with respect to the Fermi energy. So after excitation, the electron takes the energy of the photon, and it has then a certain kinetic energy, which is the difference between this level and this level, and the vacuum energy. But now the electron is transferred to the analyzer. And the analyzer has a different work function. So there is a contact potential difference. And this contact potential difference accelerates the electron a little bit. So the kinetic energy you measure is this one. And the analyzer and the sample are in electrical contact. And that means their Fermi levels are aligned. Even if they are not physically in contact to each other, the Fermi levels are aligned through the cable between the manipulator and the analyzer system. Okay, and that means the Fermi levels are aligned. This is in equilibrium. So now you can get the binding energy. This binding energy is now the excitation energy minus the kinetic energy. So the excitation energy is what we know. The kinetic energy is what we measure. And then we have here this quantity, which is the work function of the analyzer. We cannot easily measure, but we can in principle indirectly measure that, and very accurately. Because what you need to do, is you simply need to measure a spectrum of a metallic sample. Yeah. If you take any metallic sample, where is it? Here, you can get states up to the Fermi energy. So you can really identify the Fermi energy. And that's here, we usually take silver. And this is the silver 1s level. And you see here, this is the Fermi edge. That's not only the thermally broadened Fermi edge, but this is a Fermi edge which is, yes, thermally broadened because it's at room temperature, but it's also convoluted with the resolution of the spectrometer system. So by measuring this Fermi edge, we can in principle also determine the spectral resolution of our spectrometer, which is mainly the width of the X-ray source. How good our monochromator is. Okay, so now by measuring this Fermi edge, we can adjust this because we know that the binding energy here should be 0. This is what we measure, this is what we know, and we set the binding energy to 0 by just calibrating this value with this measurement. Okay, so that's a good thing. So that means we can measure the binding energies with respect to the Fermi energy. And if we now go back to the semiconductor, you see that this quantity is something which we can quantitatively measure with our technique with an accuracy of, let's say, typically 50 to 100 milli-electron volts. It's not perfect, but it's still a pretty good number. Okay, now how do we determine Schottky barriers or energy band alignment? I showed this already to you. We make this interface experiments. We measure a substrate, then we measure a sample with a very thin film on top. We stepwise increase the film thickness until the film is so thick that our XPS signal from the substrate is completely attenuated. That's the ideal situation. Now, this is our potential semiconductor spectrum. And you see from the bare substrate, we get the Fermi level with respect to the valence band maximum. So we get the Fermi level inside the band gap of the material. The other thing is, what from this spectrum we get is the valence band maximum as a function, as a distance to the core level. And that's a material which is fixed for a certain material. Okay, I see there are already some questions. Okay, let's make a break after this part and then we can go for the questions. So this is a materials constant, yeah, the distance between the core level and the valence band maximum. And what we're now doing, and that's a good thing, because when you deposit a material on top, your valence band emissions will change, because here you will have a superposition between the valence band states of the substrate and the valence band of your deposited film. This is not the case for the core level, because the core level of your film is usually different because it contains different elements, chemical elements. So these core levels are very specific to the elements. Okay, so now how do we get the barrier height? So this is the energy diagram. Here is our Fermi energy. We start with a clean substrate. So we know the Fermi level with respect to the valence band maximum. It's this quantity. And we know the distance between the valence band maximum and the core level. And now we deposit our film and we follow the evolution of the core level as a function of film thickness. We take this distance as a constant, and that means we get the evolution of the valence band maximum as a function of film thickness, which ideally should saturate. We know the band gap of the material, so we also in principle know what the conduction band is doing. And if our deposited material is a metal, we are already finished. So because this is the Schottky barrier height for the holes, and this is the Schottky barrier height for the electrons. So that's a direct determination. We don't need to look at the metal levels at all. So that would be not necessary. But if you deposit a semiconductor on top, you get also the core level of the semiconductor as a function of film thickness, which should ideally show some parallel shifts with the substrate. We know from the thick film, we know the distance between the core level and the valence band maximum of our deposited film. So that means we can in principle also follow this. the valence band maximum as a function of film thickness. And then we get, from these here, we get the valence band discontinuity. Knowing the band gap of the film, we know the conduction band of the film and also the conduction band discontinuity. So that's the idea of the experiment. It's described also in this publication. All right, so, okay. That was the part about the Fermi energy. And I saw there were a couple of questions. So let's start with that. Okay, so by subterm, there was a question, could you explain in more detail the analogy to two-dimensional electron gas? Oh, well, that's a pretty fundamental question. It was this one here. That's in principle a two-dimensional electron gas, how it is made in semiconductor junctions. Yeah, so you take two materials and you dope them particularly, and then you get the Fermi level is then below the minimum, above the minimum of the conduction band. So you get some quantized states here. And this is an interface plane. This is a two-dimensional plane. So you get here, this is a two-dimensional, let's say, a two-dimensional situation where you have the conduction bands occupied in a two-dimensional way. So that's a two-dimensional electron gas. So that's how the two-dimensional electron gas is formed, for example, at the SDO-LAO interface. That's a different thing. There is no specific relation to that. That's a common two-dimensional electron gas in a semiconductor heterojunction technology. This is such two-dimensional electron gas are the basis for this high electron mobility transistors. So this is a common technology if you want to make transistors with 3-5 semiconductors, which are for very high frequency applications. Okay. And you can switch this carrier concentrations here by applying a field. So if in a field effect, can make field effect transistors with this. Yeah, okay. So in here, because you can do also modulation doping, you can make such two-dimensional electron gases with dopants which are separated from this conducting channel. And that means you can really make transistors with extremely high mobility. Okay, I hope this answers the question. On question by Pamela, on slide 7, which is the approximate thickness of platinum to induce a clear reduction of lead. Well, okay, slide number 7. It's here. So you see, this is 4 seconds of platinum deposition. I would guess that's less than 1 nanometer. And it's not a chemical kind of reaction. So you don't need much platinum. The reason why you get metallic lead here is that these lead atoms which you deposit are coming from the gas phase, and they are isolated atoms without any chemical bonds. If they condense at the surface, they will form chemical bonds with the surface. And these chemical bonds has a binding energy of, let's say, a few electron volts. And the release of the condensation energy of these metal atoms, that's what we believe, and this is also has been proposed quite some time ago in literature, that this condensation energy is causing, let's say, some reduction, some formation of oxygen vacancies. And yeah, so thermodynamically, PCT would not react with platinum to reduce the PCT and to form platinum oxide. You also see the platinum is in principle is metallic platinum. There is not much platinum oxide there. And the amount of lead, how much that is, well, that's hard to say. I would guess it's the lead also does not necessarily remain at the interface. It may, in principle, evaporate. But I will show more experiments on this later. Okay. Tatiana asks, when you are doing XPS, how do you know where is the position of the Fermi energy? Well, it's what I explained. Yeah, there it is. We measure it. It's our calibration. It's our binding energy calibration. Yeah. We take a silver sample, and we can really quantify the kinetic energy, which corresponds exactly to the position of the Fermi energy. If we remove our metallic sample and we put a semiconductor sample there, the Fermi level is still there because everything is always in electrical contact with the XPS system, with the manipulator. And this always has the same Fermi level. It doesn't change when you put another sample there. You only have to make sure that you have an electric contact between your sample and the manipulator. And then the Fermi levels between the manipulator and the sample are aligned. So you can put, in principle, we can put insulators there. As long as they are thin enough and not charging, we can measure the Fermi level in an insulator. That's really a good thing. Okay. Next question. Sylvia. All right. On slide 6, it seems that delta ECB is equal to delta ECB. No. That's just, that's definitely not the case. There are quite many different band alignments. There can be, what I do is a symmetric alignment. That's simply because it makes drawings a little bit easier. But you can have, in principle, a staggered alignment that this one is down here and this one is also down here. So you can also have alignment where, in principle, the band gaps do not overlap at all. But this is a kind of a very strange situation, which is not very realistic. But of course, like the Schottky barrier, where you can Fermi level can in principle vary through the whole band gap. You can have also the valence band and the conduction band discontinuities vary quite strongly. So you can in principle have the conduction band down here very close to the valence band. That's also something which is possible and which appears. Yeah. All right.
Maybe we should continue, Andreas, and leave the questions.
All right, that's okay.
Thank you.
Otherwise, we take too much time on the XPS. Good. All right, so then let's go to, but I think we have in total 2 hours with all the questions, but it's okay. We can also have the questions later. Oh yeah, it's already, I see. I better take my watch there. All right, so now let's come to the models for band alignment, electron affinity rule. Now we take the vacuum level here. Yeah, so we now have here an electron affinity of our semiconductor, difference between vacuum level and conduction band. The work function is the difference between the Fermi energy and the vacuum level. So if you change the Fermi energy, you change the work function. And the distance between the valence band and the vacuum energy, that's the ionization potential. If you take the metal, you have the work function. That's the difference between the Fermi level and the valence band maximum. And in this case, the electron affinity is the same, because if you bring an electron from vacuum to the lowest unoccupied state, it's the same as the work function. And also the ionization potential is the same here. So now if you follow the electron affinity rule or the vacuum level alignment, you bring the vacuum levels into contact. But at the same time, you have to bring the Fermi levels into contact. Yeah. And that's possible in semiconductors if you get a band bending in your semiconductor, a space charge region, because the bands, if you see the Fermi levels are different. And the difference in the Fermi level, that's actually the magnitude of the band bending. And still we have the barrier heights, which are now determined by the difference in the electron affinity. So you see the work function of the metal and the electron affinity of the semiconductor So this is the electron affinity of the semiconductor. This is the work function of the metal. And the difference is the barrier height for the electrons. The band bending, that's the difference of the Fermi energies. And the difference of the Fermi energies, that's the difference of the work functions. So if you're talking about barrier heights, and that's an important quantity for the Schottky barrier, you should talk about the difference in the electron affinities and not about the difference of the work functions. That's a common mistake people are making. Okay, what if this is what we would expect? If this is the real situation, we would expect that the barrier height varies with the metal work function in principle linearly. So if you increase the work function, you will increase your band bending. And the slope here would be 1. Of course, if your Fermi level is reaching the valence or the conduction band, it will hardly move anymore. So this is indicated by these lines. For a p-type semiconductor, it would be different. If you increase the work function, the Fermi level goes down. It means the p-type barrier goes down, but the slope is also 1. So this is what we would expect. The same is true, same you can get for the Anderson model for an alignment between two heterojunctions. So you align the vacuum energies, then the conduction band discontinuity is the difference in the electron affinities, and the valence band discontinuity is the difference in the ionization potentials. So again, the band alignment determined by the vacuum alignment. And if you want to look at charge equilibration, you can make a p-n junction. Your band diagram would look like that. You can again make an n-n junction. Your band diagram would like that. But you see the vacuum levels are always aligned. There is no step in the vacuum level here. And the discontinuities in all cases are also the same. Again, we have a two-dimensional electron gas here. Okay, so this vacuum level alignment is something which is, you can observe in principle experimentally. And you can observe this for the layered chalcogenides, for example. You take these layered semiconductors like indium selenide, molybdenum disulfide. You can grow them easily on top of each other, regardless of any lattice mismatch. You see here, this is some electron diffraction, low energy electron diffraction, yes, lead. And you see the diffraction spots of the substrate. You see here the distance in the lattice contents between the substrate and the film. And then for a thicker film, you really can nicely epitextually grow that. And now if you measure experimentally, so this was done by my colleague Rüdiger Schlaf, when he was a colleague when I did my PhD. And he did that for many different combinations of layered semiconductors. And then if you measure the valence band offset and you compare, this is the measured valence band offset, and you compare the valence band offset given by the vacuum level alignment, you see that this follows very nicely. But that's a very rare situation. So this is because there's only weak chemical interactions at the interfaces. Okay. If it comes to oxides, there is a difficulty because we are using the electron affinity. And if you have an oxide, the electron affinity is not a unique quantity. Very simple. This is the first example. That's tin dioxide. So these are work functions measured as a function of the Fermi energy from UPS measurements, photoelectron spectroscopy. That's nice because you get two quantities. You get this quantity and you get this quantity. This is both comes out from the experimental measurement. And the sum of the two is the ionization energy, or you can also say subtract the band gap, you get the electron affinity. And now by looking at this, you see that there are some samples which have a high Fermi energy. This is more under reducing conditions. Your ionization potential is something like 8 eV. But if your samples are more oxidized, your ionization potential is 9 eV. And that is due to the different surface terminations of the tin dioxide. So you can get a stoichiometric surface termination. All your tin atoms are 4+. So these gray ones are the tin atoms. Or you can have a reduced surface where you have tin atoms at the surface, which are 2+ oxidation state. This gives a difference in the ionization potential, and of course, then also in the work function by about 1 electron volt. Okay, we get similar things for other oxides. You can also look at zinc oxide. So the surface termination is not the only thing. You get a very similar plot for zinc oxide with the low ionization potential of 7 eV, high ionization potential of near 8 eV. The difference now is the orientation of the films. So if you are more reducing, you usually have a 1-1-1 surface orientation. And if you go to more oxidizing condition, it partially turns around and you get an anion terminated surface. And that's also something which has been measured for gallium arsenide. You see the anion terminated 1-1-1 surface has a much higher ionization potential than the cation terminated 1-1-1 surface. Okay, so now which one do you want to take for predicting the Schottky barrier? You can take either 7.7 or 6.9. And typically, the Schottky barrier does not depend on the orientation and also not on the surface termination. So that's one example. And that is, again, we deposit some ruthenium dioxide on PCT. We deposited ruthenium dioxide and not platinum because in this case, you see there is no metallic lead. That's the advantage of using an oxide as a contact. Okay. And what you see here, these peaks, at the beginning, the peaks are very broad and asymmetric. And that's because the PCT, this was a ceramic pellet. So this is a thick sample, insulating sample, it's charging. But as soon as you put your ruthenium oxide on top, you get an electric contact. You can contact the sample from the top. And then means you have no more charging because you can provide an electric contact from the top surface. And now the peaks are sharp. These binding energies are everywhere on the surface are the same because we measure a square millimeter. And if you get a sharp peak, a symmetric peak, we know that Schottky barrier is everywhere the same. And that means, and because this is a polycrystalline sample, which exposes, in principle, any surface orientation, and that's also ferroelectric material, we also have different polarizations. So whatever you do, the Schottky barrier is the same. So that's a very clear thing that, and this is also from the other experiments we have, that we usually, in most cases, we do not observe a dependence of surface orientation, surface termination. So that means this electron affinity rule, which still gives us a good guideline for predicting if you get a high or a low Schottky barrier. Yeah, if you have an N-type, if you take a metal with a high work function, your Fermi level will be higher than if you take a metal with a low work function. That's for sure true. But it's not quantitative, and for many reasons. So you cannot take work functions of a material and in order to predict the barrier heights. This doesn't work. Actually, I was once asked, what's the work function of titanium dioxide? And in principle, that's not a reasonable question because it can be something between 4 and 6 electron volts, depending on how you prepare your surface. Okay. So this was, yeah, Mariona?
Maybe you could take some questions now.
This would be also another point where I can take some questions, yes. Maybe specifically to this. So we have to make sure that we should not forget maybe the other questions. Yeah, all right. Okay, there is one. Oh, well, I would say Timothy asks, does Schottky barrier height depend on the defect states at the interface, especially for non-epitextually grown devices? I come to that later. Maybe it's better that will become more clear later. But it would, in principle, be necessary to specify which kind of defects you mean. Yeah. Because if it's a non-epitextual interface, it does not necessarily contain defects, which have an influence on the band alignment. polycrystalline materials, if you have a polycrystalline material, every interface is in principle also single crystalline. So you have grains with different orientation, but along the grain, this is like a single crystalline interface. Yeah. And the question is, if you have one grain and another grain, if the barrier here or here is the same. And as I explained before, it usually does not. So a polycrystalline material is not necessarily something with defects. It becomes a little bit different when you look for these perfectly epitaxial two-dimensional oxide heteros systems. But that you can say that this is definitely something which is without defects. If you have, we very often make interfaces of materials which which are not epitaxial. So that means they are strongly lattice mismatched. So there must be a lot of dislocations at the interface. And I would say we don't see much influence of this kind of things on the interfaces, because what we are trying to do, we are trying to move the Fermi level as high as possible and as low as possible. And if this is possible with non-epitaxial interfaces, it means that we do not have a Fermi level pinning. Yeah, I guess that would be quite a good answer for this. Yeah. Okay, no more questions. Then I maybe.
Well, we had some question remaining from before.
From before,
yeah.
So because I still have a couple of slides to go, but.
Do you want to finish these 2 slides and do 1 more minute of questions? Or how do you want to organize?
Okay, I know I can continue with the other questions. So Shankari, she now asked if she wants to ask with the mic on, but it's I can also read the question if it's the same. So she asked, XPS is giving us the energy difference between the valence band maximum and the Fermi level. Yes. What if my conduction band is changing with doping? Yeah, and how do I change the conduction band minimum with respect to doping? One must be careful with the term doping. In semiconductor physics, you use doping usually for dopant concentrations which are in the pp part per million range, or you can say you go to doping, a 0.1% doping would be huge in semiconductors. And you can also have some degenerate semiconductors with higher doping. But if you usually take a low doping concentration, this does not affect the band gap. That's a thing. If in ceramics, in oxides, if you go to doping with which can be much higher than this 0.1%, so you can go to 5%, 10%, then you change, of course, your density of states, you change your band gaps, and you have to consider that. At the very end, if there is time, I will show the experiment we made also with Mariona's sample, and that will be one example for this.
Okay, good. So let's continue maybe a bit.
There was one more question. Maybe I can get this also from Mathieu. Is it possible to get different offsets depending on the core level you choose as a reference? If you get that, something is wrong. Then it's usually, we usually, if we have the possibility to measure different core levels, we do this. And I will also later show some example for the for Schottky barriers. If the core levels are not shifting in parallel, usually that's an indication of an interface reaction, or some extremely narrow space charge regions, different effects may occur. Usually they should give the same alignment. They should not be different. Okay. Well, I need to drink some beer, sorry. So now we come to Fermi level pinning. I think it was first published by Bardeen in 1948. Bardeen is very famous. He was one of those who made the first transistor. And also the one that made the theory about this, the BCS theory of the superconductors. All right, so let's look for the barrier height and the dependence of the barrier height on work function. For the electron affinity rule or the Schottky behavior, we would expect that this varies with a slope of 1. But very often, and especially for silicon, you find out that the slope is much less than 1. And as I explained, or I emphasized, that the Schottky barrier, the barrier height, is the Fermi level position at the interface. And if the barrier height does not change as independence on the work function of the metal, that means the Fermi level is more or less always at the same energy. And that's why this is called, a low slope is called Fermi level pinning. So this Fermi level pinning is caused by defect states at the interface, interfacial defects. We will later see that this does not need crystallographic defects at all. It's an intrinsic nature of interfaces between semiconductors and metals that you get some induced gap states. These induced gap states can be charged and they form an interface dipole. And if you have an interface dipole there, your vacuum levels are no more aligned. You have a potential drop there. And this modifies the barrier height. And if the density of interface states is high, the Fermi level at the interface will not vary at all. I will show this later. What's the reason for these induced gap states? Well, you take a semiconductor with a band gap and you take a metal. And now your metal, you have these work functions. We saw this, let's call it just a sine wave. Yeah? This is the work function of the metal. Now, if you did some quantum mechanics course in your studies, you should probably have done the tunneling effect. Yeah? And when you have a tunneling effect, you know that the wave function in the semiconductor, if you have a barrier here, and this is a barrier for the electrons, then you do not have oscillating states in this material, but you have exponentially decaying states. It means the reason, let's say here it is, in the band gap, the Schrödinger equation in the band gap of a semiconductor has a solution. It's that there are no electronic states, but this is because these electronic states, the solutions cannot be normalized. And they cannot be normalized because the K vector is imaginary. So you have exponent minus ikx, and if the K is imaginary, you simply have an exponentially decaying function. And if your semiconductor is extending infinitely, your exponential function will diverge either in this direction or in this direction. You cannot normalize this. But at the interface, you can normalize it because the exponential, it doesn't increase there, it just stops. So that's the reason. It's a coupling of the work functions, of the wave functions. And this is exactly the same situation as in the quantum mechanical tunneling. So that means you get some electronic states there. And these are the induced, or particularly it's also called metal-induced gap states. And these are intrinsic to the interface states. These cause these intrinsic interface states. That's something you cannot avoid. If this is true, then the band alignment is governed by the charge neutrality levels, which is a feature of these states. So that's just an old calculation. This is by Louis et al. From 1977. So that's the interface between aluminum and silicon. So down here is the silicon. You see here, this is the band gap. That's the density of states. Here is the band gap. This is the aluminum, which shows more or less a square root density of states as for a free electron metal. If you go to the interface, you see that there is no more a band gap. The gap is filled with states. So this is a density of states which is resolved layer by layer across the interface. Okay, so these are these induced gap states. And in principle, what they could also show is that these induced gap states decay from the interface faster if you go to more ionic material. So this is for silicon, That's for gallium arsenide. Zinc sulfide, zinc selenide are more ionic. They decay more faster. And they simply decay faster because the band gap of this material is higher. And if we consider this as a tunneling, and this as our tunneling barrier, if you make the band gap larger, your barrier will increase and the decay of the wave function will be faster. This is very simple, again, quantum mechanical tunneling. So you can understand this dependency. Larger band gap, less induced gap states. That's an important thing. And this is an empirical model to calculate that. So you have an entire semiconductor, you have a metal work function, you have some induced gap states with a charge neutrality level. I explain later what a charge neutrality level is. If you do the electrostatics of this, you get this function. The barrier height is now given by S, this is our slope parameter, multiplied by the difference between the work function of the metal and the electron affinity. So this is the electron affinity rule. If the S is 1, the Schottky barrier height will be this quantity. If the S is 0, that means if you have Fermi level pinning, this will be the Schottky barrier height. And that's the Schottky barrier height for the electrons will then be the band gap minus the distance between minus this phi 0. So that's then the Fermi level will then be pinned at the charge neutrality level. This term, this is a field dependent image force lowering. Let's ignore about this. And with this model, you see that this interface index, the slope parameter, is in principle the permittivity of this, say, artificial interface layer, and it contains the density of interface states. So this equation is something which is not very difficult to implement. So I did some modeling with my highly liked IGO Pro software. You will see this soon. What do you see here? The plot of the charge density. So this is our space charge. The blue one is the charge in the interface states, which is negative here. And the black one is the compensating charge in the metal surface. So this is now the band diagram, vacuum level, conduction band, valence band, and the charge neutrality level. And this is the control panel in my simulation where I can adjust the doping concentration, which I will not do, that's not important, but I can adjust the density of states at the interface, so the degree of Fermi level pinning, and I can adjust the position of the charge neutrality level and also the work function of the metal. Okay. Oops, we are here. So that's a simulation. It's in principle the same figure as in the slide. Okay, if now I change the work function of my metal, so you see that the band bending is changing. Now we have also the position of the charge neutrality level at the interface is changing. But what you already see is that the vacuum level is always not perfectly aligned. And that's because the charge in the interface states is quite significant. If we go down with the density of interface states, so 10 to the minus 9 per square centimeter, that's not a lot. If we change the work function of the metal now, you see that there isn't any interface dipole potential, and there is also no interface density, no interface charge. So, and now the barrier height is directly following the work function of the metal. If I, let's make it small, and now we increase the density of interface states, and you will finally notice that the interface states charge is increasing, and then eventually the Fermi level matches with the charge neutrality level at the interface. And now we have this dipole here, and if I change the work function of my metal now, the Fermi level at the interface doesn't change at all. It's only the work function of the metal which is changing, and the interface dipole which is really affected. So it's really the density of the interface states which tells you if you have Fermi level pinning. In this case, we have Fermi level pinning or not. Oh, go back here. Oh, yeah. So what's a charge neutrality level? Consider silicon, it's a tetrahedrally bonded semiconductor. So we have a tetrahedral coordination, we have sp3 hybrids. These sp3 hybrids form bonding orbitals when they overlap between the silicon atoms, and anti-bonding orbitals. And the bonding ones are the occupied ones, they form the valence band, and the unoccupied ones, they form the conduction band. If you go to a surface, your silicon has no bonding partner. So that means you have your sp3 orbital, a dangling bond, and the energy is approximately that of the sp3 orbital. And this sp3 orbital is between the occupied and the unoccupied state. So it gives us an electronic state in the band gap. Now, why charge neutrality? Let's look at the occupation of this state. What do you think when this state is neutral? This is, if you take a silicon atom, each silicon atom has 4 bonding partners and it has 4 valence electrons. If you remove one bonding partner, 3 of the electrons are still shared with the other 3 silicon atoms below the surface. And you have 4 valence electrons. And the silicon atom is exactly neutral when this state is occupied with 1 electron. Then the silicon surface atom is electrically neutral. And that's actually, and when is this occupied with 1 electron? The orbital can adopt 2 electrons, and it's exactly occupied with 1 electron with the Fermi level is here, because then the occupation probability is 50%. So that means if your Fermi level is exactly where this surface dangling bond is, you have no surface charge. If your Fermi level is higher, you have a negative surface charge because you have more than 1 electrons in the orbital. And if your Fermi level is lower, you have a positive surface charge because you have less than 1 electron in the surface orbital. So that's kind of, and that means this level is the charge neutrality level. It's the level of this bond. Well, in a real semiconductor, you have not only 1 bond, they overlap, so they broaden, the density of states is broadening, but this is a minor detail. It's just to tell you that such a distribution of surface states has a charge neutrality level, and it means that the average occupation of these levels gives us a 0 surface charge. Okay, that's a charge neutrality level. That was for a surface. For the interface, it's a little bit different, but just to give you one rough idea what a charge neutrality level is. So if you have Fermi level pinning, the energy band alignment is the alignment of the charge neutrality levels. Well, in a metal, the charge neutrality level is, of course, the Fermi energy. And for if you have two semiconductors, you can get the alignment of the charge neutrality level as well. So these charge neutrality levels, although I explained it for the surface, we have to look at the charge neutrality level of our induced gap states. And these induced gap states are related to the solution of the Schrödinger equation of the bulk material, those with the imaginary K. So this is the charge neutrality level is a bulk property of the semiconductor. It's not an interface property. In the bulk, we don't need to care about it. We only need to care about these charge neutrality levels at the interface. But it's a bulk, it's a property which is determined by the bulk of the material and not by the interface itself. So that means we can draw the charge neutrality level everywhere. And if we bring 2 materials into contact, we have to align the charge neutrality levels. Okay, there are some ways to determine that. This is all DFT. You can get branch point energy. So Tejedo and Flores started in the 70s. Terzov put that on a more quantitative basis in the early 80s. There's also what is called this dielectric mid-gap energies by Cardona and Christensen's. And there's also other people using other definitions. And sometimes it's not really clear what the kind of definitions the people use. But there's different ways to obtain these charge neutrality levels. Here are just some examples for the branch point and the dielectric mid-gap energies. Okay. This Fermi level pinning by the induced gap states is a slow parameter. So here you see the not the work function, but the electron affinity of the metal, which is related. You see for silicon, you don't get much variation. For silicon dioxide, you get a lot of variation of the Schottky barrier with the work function of the metal. That's quite an old work, but the people have realized that the covalent semiconductors show stronger Fermi level pinning than the more ionic ones. And I gave you a qualitative explanation for that, which was that these materials have smaller band gaps than these ones. So the density of induced interface states is higher in this case. So we have strong pinning and weak pinning. Now, what about the oxides? I guess for this school, many people are interested in the oxides. So what about the Fermi level pinning for the oxides? Well, here the people say already there should be not much pinning, but we can also get that explicitly. So here are some, this is the band alignment between barium strontium titanate and lead zirconate titanate. The energy bands here are a little bit higher. Each data point here is a Fermi level position measured at a thin film surface of this material, or here for PCT as well. But that's not the important point. If we make the Schottky barriers for ruthenium oxide, the Fermi level with ruthenium oxide is somewhere here, and the Fermi level with ITO is somewhere here. So with ITO, we get the Fermi level which is close to the upper limit of the variation of Fermi energies, and with ruthenium oxide, we have a lower Fermi level. And the variation is in principle the same for both materials. If you go for PCT, so the work function of ITO is 4.5 eV, the work function of ruthenium oxide you measure by XPS is 6.1 or even 6.5 EV. So that means the difference in work function is 1.6, and the difference in the Schottky barrier height is here, that's about 1.1 EV. So we would expect a little bit of pinning. But this were one of our first experiments with ruthenium oxide, and we did many, many after that. And we learned that the ruthenium oxide doesn't behave at the contacts that like it has a work function of 6.1 EV, it more behaves like it has a work function of 5.6 EV. So the measured work function is a difficult thing. This is like for the ionization potentials of the semiconductors. If we take this one, the difference in work function is 1.1 EV and the difference in barrier height is 1.1 EV. So there is no pinning at all. So that means we can move the Fermi level around at the interface if we just get proper materials. And it's important that we use oxides because they don't make a chemical interface reaction. Okay. And then we have, and it's clear that we have no Fermi level pinning for these kind of materials at the interface, if you are careful not to introduce defects by how you make your interface. Here are some other examples. This is antiferroelectric lanthanum doped lead zirconate stannate titanate. We did something where we can take our material, we make a very thin electrode on top. That means we can measure the PE loop in the XPS system. So this is our antiferroelectric PE loop. And then we can stop the loop at a certain position and do XPS measurement and determine our Schottky barrier height. And again, you see this is with ruthenium oxide and ITO electrodes. It's again 1.1 EV difference. We did measurements on bismuth vanadate, which is a very important photocatalytic material. Band gap is something like, I'm not sure, about 2.5 EV or something like this, 2.4. And with our materials, with ITO, ruthenium oxide is not here, but nickel oxide, cobalt oxide, we get also a variation of the Fermi energy of 1.2 EV. And here you see, this is the shift of the vanadium peak, this is the shift of the bismuth peak, and they are the same. So this is a parallel shift of two core levels, which is really good to know that it's really a shift of the Fermi energy. All right, so that's a part for the Fermi level pinning. So the pinning means that the Schottky barrier height becomes less depending on the metal work function. And it's an intrinsic property, these induced gap states. So this is nothing, it doesn't need any crystallographic defects. That's here, they are intrinsic to that. But their density depends on the material. So not every material has a high concentration of induced gap states, so not every material gives us an intrinsic pinning. But particularly the covalently bonded semiconductor silicon gallium arsenide shows strong Fermi level pinning. And in this case, the band alignment is determined by the charge neutrality levels. And finally, for the oxides, there should be not much pinning. Okay. Time for questions. I see already one, but I first have some water. Okay. Yeah. One question by Gael. What are the parameters that influence the density of interface states? Yes. Well, I can probably talk an hour about this, but not necessary. It's for the intrinsic interface states, it depends on the surface orientation. It depends on the surface preparation. You can get this even for epitaxial interfaces. There is one very famous example for interfaces between silicon and nickel silicide, which are nicely epitaxial, which you can prepare with different surface orientations. And surprisingly, the people find that the Schottky barrier height for the different orientations and the different surface terminations, you can grow in principle the nickel silicide with 2 orientations on the same silicon surface. You get quite a substantial different barrier heights. So it's much more, one has to look more into the details in order to get this. This is not just one charge neutrality level and the Fermi level is always there. So that means also the details of the wave functions of the metal. As I say, the induced gap states are caused by the coupling of the wave function of the metal with the wave function with the decaying wave function in the semiconductor. If you change your metal, for example, by changing the orientation or by changing whatever, how you put this metal on top, the coupling will be different. And that means already it will give you a different density of interface states. It's a very detailed structural thing. There was an extensive, a very long review paper by Tang, T-U-N-G, which is explaining these kind of things. Okay, but otherwise, as I said, usually ionic materials, not necessarily a low density of interface states, but the interface states are near the band edges. And that gives you not much pinning because you can move the Fermi level in between usually quite easily. Okay. Good. Then we continue. No more questions. So if it's not the vacuum level, and if it's not the charge neutrality levels, what is important for the alignment of the energy bands of oxides? And there is something which is called the common anion rule. So the common anion rule was proposed in the, I don't remember, in the 60s or in the early 70s. And it states that if you take 2 semiconductors which have the same anion, the valence band discontinuity between the 2 should be small. Why is that the case? Where does that come from? It comes from the bonding in ionic compounds. In an ionic compound, you have your shell, for example, your anion, and you have your metal levels. And usually the anion levels are deeper in energy than those of the metals. And then you form an ionic bond. This is the bonding combination, and this is the anti-bonding combination. And just due to the physics of this bond, this state is mostly determined by the anion because they are closer in energy. And this one is only determined by the metals, because this is this is close in energy to this one. If you go to the extreme case, 100% ionic bond, it is also clear. The metal transfers its electrons to the anion, and the anion orbital is occupied, and the occupied states are in the valence band, and the metal orbitals are unoccupied. So and the metals and the unoccupied states form the conduction band. That's why the states here are made up by the anion states. And now you can look at, for example, what are these energy levels for? This is for the chalcogenides: oxygen, sulfur, selenium, and tellurium. These are the P levels. And you see that they go down in energy. And now look at the valence band alignment of these two materials. This is a calculated one, but experimentally we reproduce that very, very nicely. So this is cadmium telluride and zinc telluride. First of all, you see the two are really very similar energies. Also, the two selenides, zinc and cadmium selenide, have very similar valence band maxima. Cadmium sulfide and zinc sulfide have very similar valence band maxima. And you see also the tellurides, selenides, and sulfides, they go down in energy just like this. So that seems to be a principle. This is a very simple rule. Yeah. Okay. So this is energy band alignment of chalcogenides. So this is all our experimental work and also combined with some theory works. So this is reviewed in this paper. Again, you see the telluride, selenide, sulfide, it's the same thing. And the oxides are usually, they are also down there. Now there is copper indium selenide, copper gallium selenide, and copper indium sulfide. They are, surprisingly, the copper indium selenide valence band is not here. It's, although it contains also a selenium. And the reason is that in copper indium selenide, we do not have only selenium, which contributes to the valence band, but also copper. Copper has a very shallow 3D level. And this is just about 2 or 3 eV below the maximum of the valence band. And the copper states, the copper D states hybridize a lot with the selenium states. And this is what is called, what Alex Zunger in his papers is calling PD repulsion. So that means the valence band maximum is just higher in energy, about 1 EV if you add the copper here. And then there are some other materials which also have cation, they all have cation contributions. So, but the materials where really you can have only the anions in the valence band, they really nicely follow this common anion rule. You can get the same thing for the oxides. You see here the valence band maxima, and these are many oxides which contain in principle only oxygen states: tantalum oxide, aluminum oxide, strontium titanate. One exception is the rutile titanium dioxide, which is a little bit higher in energy. This comes, to explain the details, I will do on the next slide. And then there are, this is copper oxide with the 3D orbitals, also iron oxide. It has a partially filled 3D shell. So again, you have here not only oxygen 2p, but oxygen 2p and iron 3D. Yeah. Surprisingly, also the lead titanate and the lead circonate, and also even bismuth oxide, sodium bismuth oxide. Bismuth ferrite is a different case because it contains bismuth and iron. But all these materials which contain occupied 6s states, they also show higher valence band maxima. So yeah, so the bismuth has in principle 5 valence electrons, but to ionite to get bismuth 5+ is quite difficult because the 6s electrons are very much stabilized in these compounds. Okay, so common anion rule is fine as long as no other species contribute some density of states to the valence band. So what about the titanium dioxide? This was our measurement. So we did, again, interfaces with ruthenium oxide and ITO. And we find that the anatase is about 0.7 eV lower than the rutile. We got some theory which showed exactly the same thing. So that's in principle, that's both titanium dioxide, anatase and rutile. This is in principle a different polytype. What is different in the polytypes is the overlap of the non-bonding pZ orbitals. So in rutile and in anatase titanium dioxide, the oxygen is sp2 hybridized. So it forms in principle a planar structure and all the bonding is in plane. The pZ orbital is out of plane. And now in anatase and in rutile, the overlap between these pZ orbitals is different. And in rutile, you have a stronger overlap of the pZ orbitals of some neighboring oxygen atoms. And the stronger overlap gives a wider splitting of the piece of this band. So these are the energy bands projected onto the contributions of sp2 and pZ orbitals. This was done by Paul Erhardt in Chalmers using some Wannier function analysis. And then you see that's exactly the pZ orbital, which shows really for a non-bonding orbital an extremely high splitting. Yeah. And that gives, this is the reason why in rutile the valence band maximum is higher than in anatase. The valence band maximum of anatase is the black line here. So this common anion rule, one has to be careful when you go from one polytype to another. So that can really make a difference. Okay, so for this one, as long as the common anion rule seems to be valid, as long as the valence bands are formed mostly by the chalcogen B states. But we still have to take care about this, about the different polytypes. Okay, cation contributions to the valence band shift the valence band maximum upwards, and the candidates for that are especially copper and silver d orbitals, partially occupied d shells, so that means iron oxide, copper oxide. In principle, all of these transition metal oxides, all of these many perovskite materials, lanthanum ferrite and things like that, they all have higher valence band maxima. But also the S bands, not only the 6S, lead and bismuth, also the tin. Tin dioxide is a tin 4+, and the 5S is empty. If you go to tin monoxide, SNO, then the FS orbital is occupied. It's not a very stable compound. It really very much likes to disproportionate into metallic tin and SNO2, but you can make it. And it's at the moment the best candidate for making a P-type thin film oxide transistor. Okay. Any questions here? Urgent questions? I probably have something like 10 more slides or so. Yeah, okay, that says, there's one by Felix. How did you experimentally stabilize the rutile and anatase phase without introducing defects? Well, rutile was easy. We just bought some single crystals. And for the anatase, actually, what did we do there? There are some certain deposition techniques where you can get directly some anatase phase. And I think at the end, we also had some anatase single crystals, but you can distinguish the anatase and the rutile phase from the distance between the valence band maximum and the core levels. So this is also explained in this publication. So it's in principle, and also we have some structural characterization. Well, for the single crystals, it was very clear. But for the thin films, they're usually their anatase. And there we can very nicely make that. I guess we also measured some films from Juan Biscard, who was our first speaker. Okay, so we didn't make that by ourselves.
Yeah, so Andreas, now we start to be over time. It's okay if you have 10 more slides, it's 10 minutes, and then we shorten the question time. Is that okay with you?
All right. Well, my idea was to have in principle all the questions in between, but it's okay. Right. I can try to be faster for the rest. Yeah, if there are more general. Yeah, no, that's okay. All right. Okay. Now you can get some defects at the interface. One example, platinum on PCT, I showed already, metallic lead. Yeah. Fermi level at 1.8 eV below the conduction band. Copper deposition, we form metallic lead. Fermi level 1.6 eV below the conduction band. It has already quite a different work function. Silver deposition, work function 4.5 eV, Fermi level at the interface is more or less always the same, but again, we form metallic lead. So that means we can deposit metals with quite different work functions. The Fermi level at the interface, it means the barrier heights are always the same because we reduce our substrate. We saw that also for tin dioxide. If you deposit platinum on tin dioxide, you also get tin 4+ and a metallic tin peak. What we now did in a near ambient pressure XPS system, we added some oxygen to the gas phase. Yeah? And when we do that, you see that the metallic tin is disappearing. And you also see that the binding energy of the tin 4+ is changing. So the Schottky barrier height is changing. We can oxidize the interface and we change the barrier height. Now we take the sample here and we simply remove the oxygen by pumping the vacuum. We do nothing else. And what you see, okay, we start here again, and you see the metallic tin is reappearing. Yeah. And again, the Schottky barrier is changing. So that means somehow the oxygen is diffusing through the interface and is oxidizing and reducing the interface and thereby changing the Schottky barrier. We can do the same thing with strontium titanate and platinum. Same experiment, you see it's going up and down depending on the oxygen partial pressure. Actually, it's only this part where the barrier height is really directly following the pressure. Then if you go to the lowest vacuum, there are the residual gas which contains some hydrogen is really getting a huge change of the barrier. Here you see blue. Green is the change of the strontium, and these blue squares are change of titanium. This is always in parallel. So again, also here, you can shift the Fermi level in principle by more than 1 eV upon oxidation and reduction. That's defects which appear at the interface. I'm pretty confident that these defects are really directly at the interface. But there's also something that if you have defects in the bulk of your material, let's consider a defect which is, let's say, a trap level, some distance from the conduction band minimum in an N-type semiconductor. Now you want to raise your Fermi level. No, you want to lower your Fermi level, so you want to have a lot of upward band bending. As soon as this trap level is crossing the Fermi level, you start to occupy the traps. And that means you change your effective doping concentration of the material considerably. And that means the space charge region is just shrinking. The width of the space charge region is then here very shrinking. So you can calculate the potential distribution, and that's 10 to the 20. That's a reasonable doping concentration for an oxide material or defect concentration. And then you see that this narrow region is just 1 or 2 nanometers. And that means the information depth of the XPS, the XPS is then not surface sensitive enough to measure the Fermi level here. You will measure somehow an average of the Fermi level. And if it's even narrower, in principle, you measure the Fermi level position here and not here if you have a high defect concentration. So that's the simulation of the spectra, how they would look like. You could really see how much, this is the Schottky barrier, and you see how much the defect levels are changing. And ideally, this is a possibility to determine the trap energy, which would be here, yeah, or here. And that's just how to plot the barrier height as a function of trap. This is not only an artifact of the XPS, this is in principle the same for the electrical properties. Because if you have such a narrow space charge region, you have a very huge electric field. It's not only that you get tunneling here, also the image force lowering is substantial. So we did a calculation for zinc oxide, and actually the effective barrier we measure by XPS and the barrier you get by the image force lowering is pretty much the same. So you have to be careful about such defects. And we have a lot of, okay, I can skip that. And that's, we get when we measure the interface between copper oxide and zinc oxide. We measure valence band offsets of 1.5, 1.6, 1.9, 2.7 eV, depending on how we make the material. And you can see that, you see, for example, in the copper oxide, if you make the copper oxide in a slightly reduced state, your Fermi level is pinned near 0.5 eV and you don't get much band bending. If you make it at higher energies, with the more oxidizing conditions, you had a different Fermi level, and now you can have some band bending in a copper oxide. And that can give rise, and the same with the zinc oxide, we also have oxygen vacancies, which can pin the Fermi energy because there are deep traps there. So they can lead to this modification of band alignment. And also for zinc oxide, we have also seen this directly for Schottky barriers. Now the bismuth ferrite, the cobalt doped bismuth ferrite. So this is a sample which was doped with 10% of cobalt. So these are the cobalt 2p spectra. This is the sample after cleaning. And we see from this satellite peak, we can get the oxidation state. So this is cobalt 2+. Then we oxidize our sample by an oxygen plasma treatment. And we get a cobalt 3+. And if we reduce the sample, which we do by water adsorption, we get a mixture of cobalt 2+, cobalt 3+. In principle, you also see the binding energies are changing. But the changes of the binding energy you better see when you look at a bismuth 4F peak. So this is an undoped bismuth ferrite sample, no cobalt. This is the starting condition. This is after oxidation. And this is after reduction. And you see how after oxidation, the Fermi binding energy is reduced. That means the Fermi level goes down. After reduction, the Fermi level goes up. And what you see after reduction, that means water adsorption, you see metallic bismuth. So that means we have really reduced, chemically reduced our sample, but also had a lot of Fermi level shifts. The cobalt doped samples is similar. The oxidation shifts to lower binding energies, and after reduction shifts to lower binding energies. So these three spectra corresponds to these samples, to these measurements. But in this case, there is no metallic bismuth. And if you look at the binding energies, even here after reduction, the binding energy, the Fermi level is not as high as in principle for the clean surface when we have the cobalt 2+. And this is for, and you see that the sample which is really reduced, where we see the metallic bismuth, now the Fermi level is really much higher than for this cobalt doped sample. So that's a situation for the bismuth ferrite. So our Fermi level can vary like this, and we get until we reduce our bismuth, we also reduce the iron. So that would kind of be an upper limit of the bismuth ferrite. If we add a cobalt, the Fermi level can only vary in this range, at least after the oxidation of the sample, because the cobalt because here the cobalt is 3+. If you want to raise the Fermi level further, you first have to reduce the cobalt. So this doping can prevent the reduction of bismuth and iron, because by the confinement of the Fermi energy. Okay, so that's really a nice example where we can combine chemical changes and electronic changes. And our interpretation of these data is that the reduction of the pure bismuth ferrite is caused by that we get metallic bismuth and iron because we raise the Fermi energy too much. Okay, similar things happen at copper oxide when we deposit ITO. You want to make copper oxide is a perfect material for solar cells. 1.5 eV band gap, it's a dream. Very simple to make, very cheap material, very abundant material. A dream to make, but it doesn't work. And probably a main reason for this is that you cannot go with the Fermi level up here. There's no way, because copper oxide, copper monoxide is not stable with the Fermi level here, because if you raise the Fermi level, you reduce the copper. And we can show that by depositing ITO. you see this satellite peak. This is a characteristic feature of the copper 2+ oxidation state. And if you deposit ITO, the Fermi level goes up, we bend the bands down, the copper 2+ disappears. Okay, the similar thing happens for Cu2O and for copper gallium oxide. Also, this is a very nice material with 1.5 eV band gap, but also you do not only have the problem that the copper is reduced when you go up, but also that in this case, if you want to go down, you also oxidize the copper. So the band gap is not necessarily the relevant quantity for guessing the photovoltage. You need to know how much you can split the Fermi energy. And these valence changes of these transition metals, that can be a very important drawback for getting large changes of the Fermi level. Just to convince you that this is really important, here are some experiments, just some simple sketch, how we made some films, how we made the solar cells, and we measured efficiencies and photovoltages. And the photovoltage you get is pretty much related to the maximum splitting of the Fermi level we see in our XPS measurements. So our experiments can really reveal how high we can go with the Fermi energy and also how low we can go with the Fermi energy. And understanding this is really very important for making good devices. Okay, there was a question about oxygen vacancies, but maybe I can skip that. Well, I take it. It's a good thing. We made diodes. One contact was ITO. It's an ohmic contact to strontium titanate, and we made platinum, which is a barrier. And we compared niobium doped strontium titanate, and we did also an iron dope, which is an acceptor doping, which is usually an insulator. But we reduced the iron doped strontium titanate so that it becomes almost as conductive as the niobium doped one. You see, this one doesn't show any barrier, but only the niobium doped one really shows a rectification. Okay, so what happens? So that's our barrier with the platinum, and that's our oxygen vacancy concentration. In the iron doped strontium titanate, this is high. This is a logarithmic scale. In the niobium doped strontium titanate, there should be almost no oxygen vacancies. Almost no, much less than here. If you equilibrate that, because you have a potential barrier here, the concentration of the oxygen vacancy will follow the potential. This is electrons are here depleted. That means negative charges are depleted in the space charge region. And that means positive charges like oxygen vacancies would be accumulated. So after equilibration, you see that the oxygen vacancy concentration at the interface is enhanced. And if you have already a lot of in the bulk, the enhancement will become so high that in principle you make a metallic material. And at the end, with the iron doped strontium titanate, which has a lot of oxygen vacancies, and the movement of the oxygen vacancies towards the interface makes this barrier extremely narrow. And that means you don't get a barrier. So you need maybe some 100 degrees C in order to get the oxygen vacancies mobile, but that is something which you have to consider. So if you have mobile defects, and that depends on the temperature and the kind of the defect, you can also substantially modify your barrier height. Okay, that was about the defects. These are now extrinsic defects, not the induced gap states. They can substantially modify the barrier heights, in particularly for the oxide materials. And there's various ways you can get defects at the interface, for example, by metal deposition, which you can get easily rid of by, for example, heating in oxygen. But also if you have bulk defects, they can be very important. And a funny thing is that it does not necessarily be a crystallographic defects, because if you have these transition metal oxides and they change their valence, that is to be considered as a defect at all, also as a defect. And these defects are present in huge concentrations. Every unit cell contains a defect. Give you you have to think about this. So that's that can be quite a severe thing. Okay, that's my last slide. Happy to take any more questions, also after 1 o'clock. Thank you. Good, thanks, Andreas, for this nice talk. Yeah, maybe we can start with this very last question of Irina Spasovejic. Is there any possibility that the changes in the binding energy of core levels after oxidation come from change of polarization of PFO? Yeah, good question. My feeling is no, and my experience is no. In order to do so, you need to intentionally change polarization. We can do that. Oh my God, too much animations. It's here. This is where we change polarization, and you see there was no change. So for the bismuth ferrite, yeah, because we don't have a metal contact on top, it's not clear. We can in principle not exclude the polarization. Yeah, especially when we oxidize and reduce the surface. But this would not lead to a reduction of the material. That's another thing, because what we saw is with the bismuth ferrite, I just go faster. So this reduction would have not been induced by the polarization. It's just an electrochemical process, so which tells us that it's really the Fermi energy which is changing. And we see in principle very similar effects with non-ferroelectric materials. So that means we have no reason to believe that this is caused by the polarization. But of course, it would be nice to check that separately. Okay, so we have another question from Gael. Do you use other techniques besides XPS to measure energy levels? We measure some defect energy levels also with electrical measurements. Yes, we do. We in principle, we obtain activation energies. This is something which is very similar to semiconductors. You get the defect energy levels you can measure quite accurately with electrical measurements, and we can. But this is something which is still in development. So because all these defect levels, there are many of them where they are in the band gap, and they are so important, they are barely known. And to my feeling at the moment in these kind of materials, XPS is still a pretty good option to get some hands on these things. Yeah. And okay. From the activation energy measurements, we also get some levels for iron in strontium titanate and barium titanate. Yeah. Yeah. Okay. I have a question myself regarding XPS and defects. So some people try to rely on XPS to identify oxygen defects, oxygen vacancies. What are your thoughts on that? To be frank, literature is full of bullshit regarding oxygen vacancies and XPS measurements. Thank you. If you look at the oxygen 1s peak, there is, in most cases, it has a shoulder at high binding energy sites. Yeah. Yeah. Here. In this case, not. That looks pretty symmetric, but this is already a little bit asymmetric. But if you take the sample and just bring it inside the XPS system from air, there will be a peak. And that's simply adsorbed water or adsorbed hydroxides, surface species. If you really clean your surface, these shoulders, which are usually attributed to oxygen vacancies, are gone. Yeah, and it's there may be some materials, but I guess mostly transition metal oxides, where such a shoulder can be related to oxygen vacancies. My first argument always is a vacancy cannot emit an electron. And what we see here, these are electrons emitted from oxygen atoms. And I take a shoulder which is emitted from an oxygen atom to say that there is an oxygen vacancy in the material. That's pretty strange. Okay.
Okay, good. So yeah, we have another question related to this topic from Pamela Machado. She asks, how else could we easily detect oxygen vacancies?
Wow. Well, from my perspective, I could say we can look at the Fermi energy. If you change the oxygen vacancy concentration, you change the oxygen vacancy concentration. And then in some cases, if you have a material like strontium titanate or barium titanate, you can look at the electrical conductivity. So the electrical conductivity will depend on the oxygen vacancies. But that becomes more difficult when you go to polycrystalline materials, because the potential barriers at the grain boundaries will make it more difficult to extract this. You can do oxygen 18 exchange experiments with SIMS. That's a possibility to see what the oxygen vacancy concentrations are. And in some materials, you can also do luminescence measurements, because as again in strontium titanate, oxygen vacancies are giving a luminescent signal. Yeah, very important, but question, but very difficult to really get a hands on this. Yeah.
Okay, so yeah. Okay, here another question from Josep Fontcuberta. Band alignments are determined in dark. How relevant are photocarriers in photovoltaic operation modifying band alignment?
Okay, there was another question about oxygen vacancies from Irena. Maybe I go first to that. Okay. And she asks whether we can get from a shoulder in a titanium. So here's the titanium peak, and if you see a shoulder here, that means you have titanium 3+. And this titanium 3+, yeah, this is a reduced titanium. And that can be, of course, if you reduce titanium dioxide, that can be caused by oxygen vacancies, or is very likely caused by oxygen vacancies. So in this case, it makes sense but what you see is actually, you have to be careful. You don't see the oxygen vacancy. You see that you have titanium 3+. This may also be caused in principle by some electron trapping effects. Yeah, if it's a self-trapping effect, that does not automatically mean that the shoulder does not automatically mean that you also have oxygen vacancies. But for titanium dioxide, I guess that's really, really good. Yeah. Okay, now the question from Pep. Band alignments are determined in the dark. Not necessarily. We can illuminate our samples. And as I said at the beginning, what is the Schottky barrier? Illumination will cause some carriers in a concentration which are too low to affect the band structure. So it will not affect the band alignment, I would say, and it will not affect Schottky barriers. What may happen is that if you have a material with defects, maybe let's say it's zinc oxide, and you illuminate the sample, you form electron hole pairs, and the electrons can be trapped in the oxygen vacancies. And this can cause an effect which can cause to an effect which is very similar to what I have explained here at the very end. Yeah. where is it? This one here. Then you have a trap level, and it makes a huge difference whether this trap level is occupied or not. That is something what illumination can do. There is also effects which are related to what is called light soaking. This is in copper, indium, gallium diselenide solar cells. And there is two effects, two possibilities to explain the light soaking. The one is copper diffusion, and the other is the filling of selenium vacancies by electrons. That is something which can happen. But again, I would say it does not, it is changing the potential distribution in the space charge region, but it's not changing the band alignment. Because to change the band alignment, you have to change the chemical bonds.
Okay, so maybe Pep, if you want to unmute yourself because you had some other questions pending, like this, we do it all together.
I've only one question, very short question. Could you repeat, please, Andreas, why the Fermi level pinning appears not to be relevant in oxides? Could you please repeat the statement?
Yeah.
So the argument.
Sorry. I have seen this question in the chat. Yeah.
No, don't worry.
Well, it's let's say the qualitative simple argument is the band gap. Yeah. And you see, because it's the density of induced gap states. This is like this tunneling, yeah, quantum mechanical tunneling. You have the exponentially decaying wave function. The wave function is, and in principle, the integral over this exponential function gives us approximately something like the density of induced gap states. So that means if your wave function is decaying slower, you will have a higher density of gap states. And that's something which is shown here. So this is the distance from the interface, and that's the density of the induced states. And you see that for silicon and gallium arsenide, they are decaying much slower. And they are decaying much slower because they have smaller band gaps. Yeah. Because this tunneling barrier will increase when you increase the band gap. And that means it will decay faster. But that's a very qualitative argument.
No, but I see the answer. Thank you.
So a good test case would be an oxide with a band gap of 1 eV without any other defects. But I guess there is nothing like that. You need to go to transition metal oxides, and then there are many other effects appearing there.
No, but thank you. That's not, I understand the physics what you are talking about. Thank you. It was a very interesting talk. Thank you. Maybe it's time to Mariona.
Yeah, maybe we can close the session, I think.